Hello my dear students. In this class I am going to solve previous year Neet questions on the topic nuclei. The first question is the half-life of radium. The half-life of radium is 1600 years. The fraction of sample of radium would remain after 6400 years. We know the formula. N is equal to N naught divided by 2 to the power of T divided by T. Here, from using this formula, the half-life of radium is, that is 1600 year, capital T. The fraction of the sample of the year, this is small t. Substitute these two values in this equation. We get N is equal to N naught divided by 2 to the power of 6400 divided by 1600. 64 divided by 16, this is N naught divided by 2. This is 16 into 1 and 16 into 4. N naught divided by 4. We get N naught divided by 16. 2 into 2 into 2 into 2. It is 16, which is equal to 1 by 16. The fraction of the sample of radium would remain after 6400 years is 1 by 16 times. This is option D is the right answer. And the next question is the decay constant. The decay constant for the radioactive isotope of cobalt 57 is 3 into 10 to the power of minus 8 per second. This is the decay constant lambda. The number of disintegration taking place in a milligram means that is 10 to the power of minus 3 gram milligram of pure cobalt 57 per second. We know that the rate of disintegration per second, that is dN divided by dt. dN by dt is equal to lambda into n. Here lambda is the decay constant, n is the number of atoms in 1 milligram. But according to the Avogadro hypothesis, the cobalt contains, or 57 gram of cobalt contains 6.02 into 10 to the power of 23 atoms. 6.023 into 10 to the power of 23 atoms. But 1 milligram, that is 10 to the power of minus 3 gram. 1 milligram of cobalt contains 6.02 into 10 to the power of 23. 6.02 into 10 to the power of 23 divided by 57 into 1 milligram, that is 10 to the power of minus 3. We get the value N is equal to 6.02 divided by 57 into 10 to the power of 20 atoms into 10 to the power of 20 atoms. From equation 1, substitute the lambda and n value in the equation number 1. Lambda is 3 into 10 to the power of minus 8 second into the 6.02 divided by 57 into 10 to the power of 20. 10 to the power of 20. We get the answer 6.02 into 3, that is the 18.06 divided by 57 into 10 to the power of minus 8 into 20, that is 10 to the power of 12. Here 18 divided by 57, it is nearly about 3 into 10 to the power of 11. 3 into 10 to the power of 11. The option B is the right answer. And the third problem is the radius of iodine. The radius of iodine, atomic number 53 and mass number 125. The radius of iodine, atomic number 53 and mass number 125, nucleus is approximately. The nucleus is approximately. The radius of the nucleus, we know the formula, R is equal to R naught A to the power of 1 divided by 3. A is the mass number. Therefore, R is equal to R naught, that value is 1.4 into 10 to the power of minus 15. Here the mass number is 125. 125 whole to the power of 1 by 3. We get 1.4 into 10 to the power of minus 15 into 125 whole to the power of 1 by 3. It is 5 into 5 into 5, 125. Yeah, we get the answer 5. Now 5 into 1, 0.4. 5 into 1, 5. 5 into 4, 0.24. Finally, we get the answer. It is nearly about 7. 7 into 10 to the power of 7 into 10 to the power of minus 15 meter. Always the radius it is in the order of Fermi. Here the option C is the right answer. Option C is the right answer. That is 7 into 10 to the power of minus 15 meter. It is the value of the radius of iodine and atomic number 53 and mass number 125. It is the approximately value. And the next problem is the density of nuclear matter is nearly. The density of nuclear matter is nearly. We know the formula. Density is equal to mass divided by volume. Mass from using atomic mass number into mass of the protons in terms of kg, 1.66 into 10 to the power of minus 27 divided by volume. The volume of the nucleus is, it is assumed to be spherical. The volume of the spherical formula is, 4 by 3 5 r cube into a, or 5 r naught cube into a. When you are going to calculate from using this value or substitute the values here, 1.66 into 10 to the power of minus 27 divided by 4 into 3.142 into 1.4 into 10 to the power of minus 15 whole cube, or when you are calculating this value, we get the density. It is in the order of 10 to the power of 17 kg per meter cube. The density is constant for all the nuclei. The option D is the right answer. And the next question is, boron has an isotope. Boron has isotopes 5 boron 10 and 5 boron 11. If the atomic weight of boron is 10.81, the ratio of 5 boron 10 to the 5 boron 11 in the nature. Here, the ratio of 5 boron 10 to 5 boron 11, it is in the nature of x is to y. But the atomic weight of the boron, now we are going to calculate that atomic weight of the boron. Now that is x into atomic weight of the boron is, that is 10, plus atomic weight of the boron 11 is, that is y into 11 divided by x plus y. The boron weight is, that is 10.81 is equal to 10.81, it is equal to, or here 10.81 is equal to x into 10 plus y into 11 divided by x plus y, or this is 10.81 x plus 10.81 y is equal to 10x plus 11y, or rearranging these equations, here 10.81x minus 10x, we get the value, that is 0.81x is equal to, here 11 minus 10.81y, here we get 0.19y. Therefore x divided by y is equal to 0.19 divided by 0.81. X divided by y is equal to 0.19 divided by 0.81. Here it is in the form of 19 divided by 81. The 19 divided by 81. Option A is the right answer. And the next question is, an element breaks into element C by two-step process. An element breaks into element C by a two-step process. From A to B, it emits the alpha particle. But when this element converted from B to C, it emits the two electrons. Two electrons. Here, an element A breaks into B. An element A breaks into B. It is in the form of ZXA. Here, when it is elements breaks into C, but when it converts from A to B, it emits alpha particle. It emits alpha particle means here atomic number decreases by 2. Atomic number decreases by 2, or it is daughter element Y, and mass number decreases by 4. Then only it liberates the helium. This is equation number 1. But when an element breaks into C, again the element B breaks into C by the following process. In this following process, here Z minus 2, Y, A minus 4, this is initial nucleus. It emits. Here the atomic number is same. Atomic number is same. In this case, the mass number is reduced by 4 with the emission of 2 electrons. With the emission of 2 electrons. When we are comparing equation 1 and 2, we conclude that A and C are the isotopes. A and C are the isotopes. The option here, the A and C are the isotope. This is the right answer. And the next problem is the binding energy per nucleon of. The binding energy per nucleon of lithium 7 and helium 4 nuclei are respectively 5.60 mega electron volt and 7.06 mega electron volt. Then the energy of the reaction lithium 7 plus phosphorus, it gives the product 2He4. Binding energy per nucleon of lithium 7 that is equal to 5.60 mega electron volt, and the total energy of the lithium, it has the mass 7 into 5.60, we get the total energy of the lithium, that is 39.2 mega electron volt. Similarly, the total binding energy for that helium atom is its mass number is 4, and it emits energy, that is 7.60 mega electron volt, 7.06 into 4, we get the answer 28. 7 into 4, 28. 28.24 mega electron volt. 28.24 mega electron volt. Hence, the total energy of the reaction is energy of the lithium minus 2 times of, here it is in the form of 2He4, 2 times of energy of the helium. We get the answer here 13.2 minus, this is 28.24 into 2, 56.48. We get the answer minus 17.28 mega electron volt. 17.28 mega electron volt. It is about nearly 17.3 mega electron volt. Option D is the right answer. And the next problem is the total binding energy of deuterium, helium, iron and uranium. The total binding energy of 1H2, 1H4, 26 or 1H2, 2He4, 26 Fe56, 92 uranium 235 nuclei are 2.22. This is the binding energy for hydrogen. This is binding energy for helium. This is binding energy for iron, and this is binding energy for uranium respectively. Identify the most stable nucleus out of the following. When you are studied the binding energy curve in your theory classes, the iron is the most stable element in the periodic table. But in that case, we draw the graph between binding energy per nucleon versus its mass number. Just we have calculated here the binding energy of that hydrogen is 1s2 is equal to 2.22 divided by its mass number is 2, we get 1.11 mega electron volt. This is binding energy per nucleon for hydrogen atom. And for helium atom, that is 2He4 is equal to the value is, the given value is 28.3 divided by 4, we get the answer is 7.07 mega electron volt. And for iron is, that is 26 iron 56, 26 iron 56, 26 iron 56 is, that is 492 divided by 56, we get the answer 8.78 mega electron volt. And for uranium, that is 92 uranium 235 is equal to 1786 divided by 235, we get the answer 7.6. Here the iron is the most stable element. Iron is the most stable element in the periodic table. Among these, the stable nucleus of the following is iron, that is 26 iron 56. Option A is the right answer. And the next problem is the binding energy. The binding energies per nucleon for a deuteron and an alpha particle are x1 and x2 respectively. The energy Q released in the reaction. And binding energy per nucleon for deuteron is, that is x1. Binding energy for deuteron, this is x1. And one proton and one neutron, then 2x1 energy is exhausted, or when deuteron nucleus is given 2x1 energy, its constituents proton and neutron becomes separate. Here similarly, 2 protons and 2 neutrons combinedly produce helium nucleus, then 4x2 energy is exhausted. From using this concept here, we can write this formula 1H2 plus 1H2, it gives the product 2He4 plus Q. Here the energy exhausted is, that is Q is equal to 4x2 minus 4x1, we get the answer 4 into x2 minus x1. It is the simple concept. This much of energy is exhausted during the binding energy per nucleon for deuteron. For x1 and deuteron nucleus is given as a 2x1 energy. The option D is the right answer. And the next problem is the nucleus ruptures into 2 nuclear parts which have their mass numbers in the ratio of 2:1. What will be the ratio of their nuclear size? We know this formula, R is equal to R0 a to the power of 1 by 3. If from using this value, the ratio of R1 by R2 is equal to A1 whole to the power of 1 by 3, A2 whole to the power of 1 by 3. It is in the ratio of 2 divided by 1. It is in the ratio of 2 by 1, 2 to the power of 1 by 3 and 1 to the power of 1 by 3. Therefore, we get R1. R1 is to R2 is equal to 2 to the power of 1 by 3 1. Option A is the right answer. And the next question is, which of the following is most heavy stable element? Calcium, sulfur, sodium and lead. Among these given elements, from using the properties of binding energy curve, here the lead is the most heavy element. Lead is the most heavy element. This is already you have studied in your theory classes. And the next concept is, Which of the following is used as a moderator in a nuclear reaction, nuclear reactor? Here the moderator, coolant, concrete silt and neutron rods, these are the important parts in the nuclear reactor. But during the nuclear reaction, nuclear fission reaction, which of the following is used as a moderator in a nuclear reaction? Here, moderator is used to slow down the neutrons and heavy water is used as a moderator. Heavy water is used as a moderator. Generally, low atomic weight materials are used because here the uranium, cadmium, plutonium, these are the elements which are present in the periodic table, but the moderators are used to slow down the neutrons, that is the heavy water. The heavy waters are used in a moderator. The option B is the the next question is half-lives of half half-lives of two radioactive substances A and B are 20 minutes and 40 minutes respectively. Initially, the samples of A and B have equal number of nuclei. After 80 minutes, the ratio of remaining number of A and B nuclei. We know this formula, N is equal to N naught divided by 2 to the power of small t divided by capital T. Here, in this problem, for the radioactive substance A is, that is Na is equal to N naught divided by, after 80 minutes, this is the time, divided by T is, this is 20, because A and B are 20 minutes and 40 minutes respectively. AT divided by 20, this is equation number 1. For the substance B, that is N naught divided by 2 to the power of AT divided by 40, this is equation number 2. From using these two equations, the ratio of these two radioactive substances, that is Na divided by Nb, is equal to 2 to the power of At divided by 40 and whole divided by this whole divided by 2 to the power of At divided by 20. Now we get the ratio of the two radioactive substances, that is Na divided by Nb is equal to 2 square divided by 2 to the power of 4. It is 1 by 4. Option B is the right answer. Option B is the right answer. And the next problem is the half-life of radioactive nuclei is. The half-life of radioactive nuclei is 77 days. Then its decay constant is. Here we know that the formula, the half-life period. The half-life period is, that is T half is equal to, or capital T half is equal to 0.693 divided by lambda. The half-life of a radioactive nuclei is 77 days. Then it is a decay constant. Here lambda is the decay constant. Then it is lambda is equal to 0.693 divided by T half. Substitute the values here, 0.693 divided by 77. We get lambda is equal to 0.009 per day. This is the value, 0.009. Option C is the right answer. And the next problem is a radioactive element emits one alpha particle and one beta particle. Then mass number of daughter element is mass number of daughter element. When a radioactive element emits one alpha particle and one beta particle, when alpha particle is emitted from the radioactive element, the atomic number reduces by 2 and atomic mass is reduced by 4. But when beta particle is emission, there is an increase by 1 atomic number but no change in the atomic mass. Therefore, when one alpha and one beta particle is emitted from the given radioactive element, the mass number of the daughter nucleus is decreases by 4. The option B is the right answer. And the next question is the relation between lambda and T half, mean life and half life. Here T half is a half life. The relation between half life and mean life. We know the decay constant, that is 0.693 divided by T half. This is the relation between decay constant and half life. Here the decay constant is lambda is equal to 0.693 divided by T half. Now, or usually we can write this equation, lambda is equal to ln 2 divided by T half. Now T half is equal to ln 2 divided by lambda. T half is equal to ln 2 divided by lambda. The option A is the right answer. And the next problem is half-life of a radioactive element is 12.5 hour and its quantity is 250 gram. It is a mass. After how much time its quantity will remain? Here this is in the order of quantity, not number of atoms. Then we reconstruct the formula, n equal to n naught divided by 2 to the power of small t divided by capital P. That formula is now we can written as in terms of mass, that is m is equal to m naught divided by 2 to the power of small t divided by capital T, or 2 to the power of small t divided by capital T is equal to m naught divided by m. It is equal to 250 gram of quantity divided by 1 it is equal to 256. 256 divided by 1 is equal to 256. It is in the order of 2 to the power of 8. Therefore T by T is equal to 8, or small t is equal to 8 times of T. Now the small t is equal to 8 into half-life of that radioactive element is, that is 12.5. Now we get the T after how much time its quantity will remain. 12.5 into 8, that is 100 hours. Time T is equal to 100 hours. Option B is the right answer. And the next problem is a deuteron is bombarded on. A deuteron is bombarded on 8O16 nucleus and an alpha particle. This is alpha particle. A deuteron is bombarded on 8O16 nucleus and an alpha particle is emitted. Then the product nucleus is, here deuteron is bombarded with 8O16. It is bombarded with a deuteron 1s2. Alpha particle is emitted. The alpha particle 16 plus 2 is, that is 18. 18 means the alpha particle is emitted. 18 minus 4, that is 14. That element is 7n14. 8 minus 1 is 7. 16 minus 2 is 18. The alpha particle is emitted. 18 minus 4, that is 14. The new element is 7n14. The option D is the right answer. The next problem is a sample of radioactive element containing 4 into 10 to the power of 16. A sample of radioactive element containing 4 into 10 to the power of 16 active nuclei. Half-life of element is 10 days. Then the number of decayed nuclei after 30 days. We are also using the same formula, n is equal to n naught divided by 2 to the power of small t divided by capital T. Substitute, that is N naught value, number of radioactive element containing, that is 4 into 10 to the power of 16 divided by 2 into half-life after 30 days, that is 30 divided by half-life of that element is 10. Here this is 3 by 1, 4 divided by 8 into 10 to the power of 16, 4 by 8, that is 1 by 2, 1 by 2 into 10 to the power of 16, 1 by 2 is 0.5 into 10 to the power of 16. Option A is the right answer. 0.5 into 10 to the power of 16. 10 to the power of 16. Sorry, here this is value. This is the value of n, but here they are asking a sample of radioactive element containing 4 into 10 to the power of 16 active nuclei. Half-life of element is 10 days. Then the number of decayed nuclei after 30 days. The after 30 days means here delta n is equal to n naught minus n. Now substitute the values here. N naught is, that is 4 into 10 to the power of 16 minus n value is 0.5 into 10 to the power of 16. We get 3.5 into 10 to the power of 16. 3.5 into 10 to the power of 16. Option C is the right answer. Please make it correction. And the next problem is, if alpha particles are moving with the same velocity, then maximum de Broglie wavelength for, we know the formula, the de Broglie wavelength, that is lambda is equal to h divided by mv. Here lambda is maximum and m is minimum. Here the four options are given: proton, alpha particle, neutron and beta particle. In this case, the mass is minimum for the beta particle. Alpha is, or lambda is, inversely proportional to its mass. The particles are moving with the same velocity, then the maximum de Broglie wavelength. If the mass is very less, the wavelength is very high, because the wavelength is inversely proportional to its mass. Option D is the right answer. And the next problem is, the mass of proton is 1.007 unit, means atomic mass unit, and that of neutron is 1.0087 unit. The binding energy of 2He4 is, here the binding energy, first example, that is mass, binding energy for 2He4, 2 into, here the mass of the proton is 1.0073 plus 2 into the mass of the neutron is 1.0087. We get the value here, the 4.0320. Then the mass defect delta m is equal to, that is ZMP plus NMN minus the actual mass of the nucleus. ZMP plus NMN value is, that is 4.0320 minus the actual mass is 4. We get the mass defect delta m is equal to delta m, that is 0.032 atomic mass unit. Delta m is equal to 0.032 atomic mass unit. Then the binding energy Be is equal to delta m into c square. Therefore the delta m value is 0.032 into c square, that is 931 into 0.032. we get nearly about 28.4 mega electron volt approximately. That is option D is the right answer. And the next problem is, a sample of radioactive element. A sample of radioactive element has a mass of 10 gram. This is N0 sample. And at an instant of time t is equal to 0, the approximate mass after two mean lives. Here n after mean lives, that is Z is equal to 1 divided by A. But after 2 mean lives, small t is equal to capital 2 into t. Here we know the formula 2 divided by lambda, because t is equal to 1 by lambda. Now we get the formula, or we know that formula, n is equal to n naught e to the power of minus lambda into t. T is that is 2 divided by lambda. Therefore it is equal to 10 to the power of e. 10 into exponential to the power of minus 2, it is equal to 10 divided by 2.78 whole square. 2.78 whole square, it is in the form of exponential, it is equal to 1.35 gram. Option B is the right answer. And the next question is a nuclear reaction. A nuclear reaction is given by, it is in the form of ZXA. Its atomic number is increases by 1. When it converted into daughter nucleus, parent nucleus is converted into daughter nucleus with the emission of electron and anti-neutrino. Nucleus ZXA is changes into, where it changes into Z plus 1 Y into A, emitting an electron with an anti-neutrino. So it is a beta decay process, because beta decay means it is the process in which atomic number is increases by 1 with the emission of electron and anti-neutrino. The option B is the right answer. And the next problem is the half-life of radium is about 1600 years of 100 gram of radius existing now. 25 gram will remain unchanged after. In this case, T half half-life period, that is T half is equal to 1600 years. After two half-lives, T is equal to 2 into T, that is 2 is equal to 1600. We get 3200 years. Option B is the right answer. And then the next problem is a bomb of mass 30 kg at rest. Here this is the bomb of mass 30 kg at rest, V is equal to 0. Explodes into two pieces of mass 18 kg and 12 kg. The velocity of this 18 kg mass is 6 meter per second. The kinetic energy of the other mass. Here 30 kg, it is initially at rest into 0, and this is in the form of m into v. Now here it is converted into m1 v1, that is 18 into 6 meter per second, plus m2 v2 12 into, that is v2. Here we get 13 into 0 is 0, 18 into 6, or here v is equal to minus 18 into 6 divided by 12. This is equal to minus 9. Velocity parts explosive is of mass 12 kg. This is the 9 meter per second. Then the kinetic energy is, it is equal to half mv square. Now substitute the values here. 1 by 2 into mass, that is 12, into velocity v is minus 9 whole square. When you are substituting all these values, 12 into 1 by 2, that is 6. 6 into 9 into whole square is, that is 81. 81 into 6, we get 486 joule. The option A is the right answer. And the next problem is in a radioactive material, the activity at a time t1 is R1 and at a later time t2 it is R2 if the decay constant of the material is lambda. We know this form, R is equal to R naught e to the power of minus lambda into T. For the radioactive material, the activity at a time t1, that is R1 is equal to R naught e to the power of minus lambda into T, and R2 is equal to R naught e to the power of minus lambda into T. The ratio of these value is R1 by R2 is e to the power of minus lambda t divided by e to the power of minus lambda into t. Therefore, e to the power of minus lambda is t1 and t2. Now, minus lambda is t1 minus t2 and r1 is equal to r2 into e to the power of minus lambda t1 minus t2. t1 minus t2. r1 is equal to r2 e to the power of minus lambda t1 minus t2. The option C is the right answer. The next question is the binding energy of deuteron is 2.2 mega electron volt and that of 2 helium 4. Then the energy released during this reaction. Here the binding energy of the deuteron means it is a nuclear fusion reaction. In this reaction the minimum energy is released, that is 28. Therefore energy released is equal to 28 minus 2 into 2.2 minus 2 into 2.2. We get 28 minus 4.4. Here 23.6 mega electron volt. Option D is the right answer. And the next problem is the energy equivalent to 1 atomic mass unit. 1 atomic mass unit means 1 by 12th of the actual mass of the one atom of the carbon. Here 1 atomic mass unit is equal to 1.66 into 10 to the power of minus 27 into c square. It is equal to 931 mega electron volt. Already we have studied in your theory classes from using Einstein mass energy relation E equal to mc square. 1 atomic mass unit is equal to 931 mega electron volt. Option A is the right answer. And the next problem is two radioactive substances A and B have decay constants 5 lambda and lambda respectively. At t equal to 0 they have the same number of nuclei. The ratio of nuclei of A to B will be 1 by exponential whole square after a time interval. Here the radioactive substance of A and B. For A, it is the K1 is equal to 5 lambda and K2 is equal to lambda only. For this substance A, 5 lambda. For the substance B that is lambda only. When time t equal to 0. Here in this case n is equal to n naught. It is equal to n naught e to the power of minus k into t. But the ratio of Na divided by Nb is equal to n naught e to the power of minus 5 lambda into t divided by n naught e to the power of minus lambda into t. Here it is in the form of 1 divided by e square. Therefore e to the power of lambda t minus 5 lambda t, it is equal to 1 divided by e square, or it is equal to 4 lambda t is equal to 2. Then t is equal to t divided by, or t is equal to 2 divided by 4 into lambda. Therefore 1 divided by 2 lambda. Option D is the right answer. And the next question is, if the nucleus of 13 aluminum 27 has a nuclear radius of about 3.6 Fermi, then 52 Te125 would have its radius approximately. We know the formula to calculate the radius, that is r is equal to r naught a to the power of 1 by from using this formula, R is equal to R naught A to the power of 1 by 3, that is 1.3. 1.3 into 10 to the power of minus 15 into A value, that is 125 whole to the power of 1 by 3. Here 1.3 into 10 to the power of minus 15 into 5, 5 into 1, 5, 5 into 3, 15. It is nearly about the answer 6.0 into 10 to the power of minus 15. Option A is the right answer. Then two nuclei have their mass numbers. Two nuclei have their mass numbers in the ratio of 1:3. Then the number of their nuclear densities would be. Here the two nuclei have their mass numbers in the ratio 1/3. Density, it is mass per unit volume. The mass is directly proportional to its volume. Then the ratio of their nuclear densities. The ratio of the nuclear density, here it is in the form of 1:3. Option B is the right answer. And the next problem is, if a radius of the 23 aluminum 27 or 13 aluminum 27 nucleus is taken to be or aluminum, it is unknown value, then the radius of 53T125 nucleus is nearly. This is also from using the same formula, R is equal to R naught A to the power of 1 by 3. It is the formula to find the radius of the nucleus. But here radius for TE and radius for AL, it is equal to the ratio of 125 divided by, for aluminum is only 27 whole to the power of 1 by 3. We get the answer pi divided by 3. Then the radius for TE is 5 by 3 into AL, or of 5 by 3 into AL. Option B is the right answer. And the next question is, the half-life of a radioactive substance is 30 minutes. Is 30 minutes half-life. The time taken between 40% decay and 85% decay of the same radioactive substance. Here for the 40% and 60% the time is T1, and for 85% it is in 15%, this is T2. We know the formula, T1 is equal to 3.T2 T half log base 10 into 1 divided by 60%. T2 is equal to 3.32 T half into log base 10 1 divided by 15%. 1 divided by 15%. When you are calculate from using the log, finally you get the answer 60. Option D is the right answer. And the next problem is, a radioactive material A has a decay constant 8 lambda and B has a decay constant lambda. Initially they have same number of nuclei. After what time, a ratio of number of nuclei of material. Here this is for A material and this is for B material. Here for A material, time T is equal to 0. For the A material is N0. This is also N0. In this time the decay constant is 8 lambda, or here is lambda. When time T is equal to, in this form we get Na is equal to N0 e to the power of minus 8 lambda into T. Therefore Na divided by Nb is equal to 1 by E, and Nb is equal to N0 e to the power of minus lambda into t. The ratio of Na divided by Nb divided by Na is equal to N naught e to the power of minus lambda into t divided by N naught e to the power of minus lambda into t. It is equal to 1 divided by e, and e to the power of 7 lambda into t, e to the power of 7 lambda into t is equal to e to the power of minus 1, and 7 lambda t is equal to minus 1. Therefore t is equal to minus 1 divided by 7 lambda. Time never be negative, that's why question is not correct. Question is not correct, but here the option C is the right answer. Option C is